For this first one, fourth root, if you do 16, you're going to get 4 2's, right? So the fourth root of 16 is 2. For the a's, you're going to say 4 divided by my index, which is 2. Divided by my index, which is 4. That is 1 with the remainder of 0. So 1a came out, 0 a's stay in. Because that is an odd power, but it was an even index, I need absolute value there because a could be negative and then that would cause a problem inside my root. All right. So we can't have a negative root of a positive number. That's not going to work. We're talking about primary roots. And then b, I'm going to do the same thing. B is going to be 8 divided by 4, which is 2 with the remainder of 0. 2 b's came out. No b's stayed in. The b that came out was squared. It will always be positive because it is an even exponent, so we didn't have to put absolute value there. For this one, yeah, this is not a perfect root, so you can use your factor tree if you need to here. So if you did your 20, you should have done something like this. A 2 is going to come out. A 5 does not group, so it stays in. For my x's, I'm going to say 8 divided by 2, which is my index. That's 4, remainder of 0. 4 come out, 0 stay in. And then for my y's, I'm going to do the same thing. I'm going to say 5 divided by 2. That is 2 with a remainder of 1. 2 y's came out, 1 y stayed in. Rational exponents. So, rational exponents. We know what exponents are. Rational numbers are numbers that can be put in a fraction form. So integer exponents is kind of what we've been doing so far at this point. Positive or negative, it doesn't matter, but we've been doing integer exponents. And so we're going to talk about rational, meaning like decimal exponents or fractional exponents. One of the examples they use is the most common of exponential functions is compound interest. So it says when $P, that's your principal, are put into an account with interest compounded annually at a rate of R, the balance A after T years is given by this formula. And so it could be any amount of years. In this case, they said 2.5 years, 2.5, which means my exponent is a decimal. All right. And so this is one of the exponential functions we're going to deal with. But we are going to start introducing rational exponents. So exponents that aren't necessarily integers, whole numbers. All right. So first, let's talk about some definitions here. In Algebra 1, it says we had properties of exponents. Properties of exponents. Remember, when you multiply like bases, you add the exponents. When you divide like bases, you subtract those. All right? And one of them that we did was a power to a power. When you have a power to a power, you multiply. And so that applies to even fractional exponents. So let's say we had x to the 1/2. If we square it, we would multiply these exponents, a power to a power. So x to the 1/2 times 2, which just gives us x to the 1 or x. All right, so x to the 1/2 is a number whose square is x. Therefore, x to the 1/2 equals the square root of x. So then in general, we have what is a fractional exponent. And that's where we get here, a rational exponent. If the nth root of x is a real number and m is an integer, if you have x to some fraction, so now we're saying the exponent itself is a fraction. The numerator of that fraction represents the exponent of this little guy, and the denominator actually represents the index of a root. So if you have a fractional exponent, you are actually talking about some root of the power of that number. You can do it either way. What this means here is you can either take it to a power and then take the root, or you can take the root and take that answer to the power, okay? But the numerator represents the exponent, the denominator represents the index. So let's look at how this helps us with fractional exponents. They want us to evaluate these, okay? Evaluate these. These all have a numerator of 1, okay? So all I'm looking at is converting these to radicals or to roots. So 16 to the 1/4. The other way we can write that is a root of 16 with a 4 index, the 4th root of 16, which we actually just did, right? So the 4th root of 16 is 2. So that is the answer to 16 to the 1/4. That's 2. Negative 125 to the 1/3. That's the same thing as saying the cubic root of negative 125. That denominator represents my index. We know the cube root of 125, it is 5, and since this guy's negative, that's going to be negative 5. Let's look at this last one. Negative 9 to the 1/2. That is the square root of negative 9. If I am talking real numbers, if this is real, then we have an issue, all right? A negative and a root. If, however, they want me to include complex numbers, like we just talked about in the last chapter, complex numbers, that would be 3i, okay? So the difference between this and the first example is, in the first example, all of your numerators were a 1. So you really just had to worry about the radical and what was going on there. Now we actually have a numerator of a 3, okay? So when we have something that looks like this, it's to a fraction. That 2 still represents the index, but it's a square root, so I don't have to worry about it. That 4 is still inside, but this 3, that is actually the exponent, okay? Now you can do this 2 different ways. You can take 4 to the 3rd power and then take the square root, or you can write it like this, the square root of 4 to the 3rd power. Those are both the same thing. If I were to take 4 to the 3rd power, that is 64. Square root of 64 is 8. Or if I were to do the root first, the square root of 4 is 2. And if I cube that, that is 8. You can do whichever one first that you want to. You can either take the root and then take it to the power, or you can take the power and then take it to the root. It doesn't matter. You're going to end up with the same answer. The answer here is 8. That's what example 3 is. It wants us to take the radical and change it to exponents, and it wants me to take the exponents and then change it back to radicals. So for this one, if I were to do something like this, I have to look at all the individual pieces. So this is the 4th root of 75, and that is 75 to the 1st power. The root of A, and that is to the 3rd power, and the root of B, which is to the 1st power. So they're not all going to have the same fractions here. You could take this even further if they wanted it in like primes. If they wanted this in primes, then you actually have 3 to the 1st power and 5 to the 2nd power, if I were to break down 75, okay? Does that make sense? You break it down, you can say 3 to the 1st power, and I have 2 5s. That's why I would write 75 in there. So if I were to look at this whole thing, breaking down the 75, I have 3 to the 1st power times 5 to the 2nd power. That's my 75. Times A to the 3rd power times B to the 1st power. And they want that, instead of under a radical, they want me to write it with fractional exponents. So I'm going to do them all individually. 3. My numerator here is that 1. My denominator is the index. 5, the numerator is the 2. The denominator, the index. A, that is going to be 3 over 3, right? 3, oh no, did I rewrite it? I'm rewriting it wrong. Look at me, I wrote that wrong, that's a 4. All right, let me fix it, because I wrote a 3. We're going to reduce that one right there. 3 to the 4th and B 1 over 4. Now here's the thing. If I can reduce it, I will, which I thought my A was going to. If I can reduce it, I will. There's only one of those that reduces. So I am going to reduce that 2 over 4. I don't want to leave it like that. So I'm going to say 3 to the 1/4, 5 to the 1/2, A to the 3/4, B to the 1/4. And that's how I would write it in fractional exponents. All right? All right, let's look at going the other direction. All right, look at going the other direction. Now, here's the thing. If they want it all under one radical, then all of your fractions have to have the same denominator. And right now they don't, okay? So right now I have 2 to the 3/5. I have x to the 4/5, and I have y to the 1/2. Right now, I can't put those all under one radical. because two of my radicals are going to have an index of 5 and one of them is going to have an index of 2, and that does not work. Okay? All of them have to have the same radical. So I need to get them all with the same denominator. So how do I get fractions to the same denominator? I just find a common multiple. What's my least common denominator between 2 and 5? 10. It's 10. So I need to get all of these to 10. I multiply that guy by 2 to get it to 10, that guy by 2, and this guy by 5. So now I have 2 to the 6 tenths, x to the 8 tenths, and y to the 5 tenths. So in this case, I'm going the other direction. I don't want to reduce. I actually want to give them to common denominators, right? And now that they all have the same common denominator, I can rewrite it all under one radical. My radical has an index for all three of them as 10. And then I have 2 to the 6th power. I have x to the 8th power. I'm only using my numerators now, and y to the 5th power. And of course, 2 to the 6th can actually be simplified. 2 to the 6th is actually 64. So now I can say 64, x to the 8th, y to the 5th. And that would be going from rational exponent to radical. So let's talk about these right here at the top. I want to take the cubed root of 8. That actually has a perfect cubed root. It is 2. For the rest of them, I'm just rewriting it. They want it in fractional exponent form. This is my numerator. This is my denominator. X to the numerator, denominator, numerator, denominator. Z to the numerator, denominator, 5 over 3. That's all I'm doing there, okay? 64 has a perfect
So for this
fourth root.
64,
we're going to actually do this guy. He does have a perfect,
no,
but not this guy. So 2. Okay. So if I'm factoring him, I do have a 2 that can come out, right? Technically, I do. But they wanted me to rewrite it in fractional form, So technically, they don't want me to take out a 2 and leave 1 in. We want to see how many 2's altogether I have there, all right? So think about it as rewriting him in fractional form to count up all of these. So I'm going to say I have 1, 2, 3, 4, 5, 6 of them. So I can rewrite 64 in prime as this, 2 to the 6th, okay? And so that is actually my numerator there, the 6. So if I were just simplifying him, I would take a 2 out, I would leave two of them inside, right? But I'm not just simplifying, I'm actually just rewriting it. So I need to know what my exponent should be. So it is 2 to the 6. So you basically think of it as in middle school when you got it in prime form and you got it in all primes. That's what you're trying to do here. Get it in all primes to a power, okay? So my prime here is 2 to the power of 6. So technically it's going to be 6 over 4, which I would reduce. This is my numerator now. This is my denominator. It is 6 over 4, which reduces to 3 over 2. Okay? For my A is going to be 8 over 4. Well, that also reduces. That is where I have a to the 2nd power. So my 6 over 4 reduced to 3 halves. My 8 over 4 reduced to 2. And then I'm going to do the same thing with my B. I have B to the 6 over 4. Once again, 6 over 4, that reduces to 3 over 2. So if I write my 64 in prime, it's going to be 2 to the 6th. So 6 over 4 reduced. A is going to be 8 over 4. Reduced is 2. B is going to be 6 over 4. Reduced, that is 3 halves. Okay, so that's rewriting that one. Let's look at this one. I had to have a common denominator. So the first three actually have common denominators, but this guy right here does not. He's 2 over 1. So that's where this 6 comes from. My denominator is 3. It is 5 to the first power, x to the second power, y to the fifth power. And then if I were to get this z with a denominator of 3, that would be z to the 6 over 3. That's where this power of 6 comes from. So this is one way to do it. Or if you simplified it, which it didn't tell you had to, but if you did simplify it, you could have pulled some y's out, you could have pulled a z out, and you could have simplified it. This is just simplified. They just took the y and the z and they simplified it like you would a radical, okay? But either one of those are acceptable. And then this just wanted the square root of 196. 196 does have a perfect root. That's 14. This wanted the fifth root of 32 squared, right? The fifth root of 32 is 2. Squaring that gives me 4. But this negative exponent, that's a property that you should remember. Negative puts it in the denominator. So instead of just 4, I would have 1/4. Had it been 32 just to the 2/5 without that negative, that would be 4. The fifth root of 32, which is 2 squared. But they wanted the negative, so that put it in the denominator. These are review. We did these in Algebra 1, all right? So when you multiply like bases, you add the exponent, right? X to some power, add. This is true even if it's fractions. X to 1/2 times x to 1/2, you add the exponents. When you divide like bases, you subtract the exponents. That's also true. It's a review, but it works also for fractions. X to the 7/2 divided by x to the 3/2, subtract it. Power to a power. That's also true. These all work just like they did with integers, okay? If you have two things within a root and you take it to a power, each one is to that power. If you're dividing two things to a root, everything in that is to the same power. Anything to the 0 is 1, even if it's a fraction. Negative exponents, put it in the denominator. That's true of fractional exponents. 25 to the negative 1/2. That is basically the square root of 25 in the denominator, right? And so that's how we get our 1/5. So all of the same properties that we learned in like an Algebra 1 class apply even if the exponents are fractions. So I will say it's easier for me to rewrite these as fractions. So if I were to look at this, I would have 36 a to the 6th, b to the 12th, and I would take all of that. How do you write 1.5 as a fraction?
1/2 or 3.
Yeah, 3/2, right? 3/2. Why is this easier? Because I can rewrite that as a radical if I need to. So I can say 36 to the 3/2, a to the 6 to the 3/2, b to the 12th to the 3/2. For this guy, I can rewrite as a radical. This is my index, square root of 36. This is my exponent, cubed. For this guy, I can multiply the 6 times the 3/2. And for this one, I can multiply the 12 times the 3/2. All right, and I can simplify it. 6 taken to the third power. So if I take the square root of 36, that is 6. If I cube that, I get 216. When I cross cancel here, I'm going to get a to the 9th power. And when I cross cancel here, I'm going to get b to the 18th power. And so even though it looks weird with a decimal, we write it as a fraction. And then for any whole numbers, change it to a radical because it's easier to think about it in radical form. What about this guy? Well, I need to take everyone to that power. 216 to the 1/3. X to the 9th to the 1/3. 125 to the 1/3. 1/3, that means the same thing as the cubed root. The cubed root of 216. Here I multiply. 9 times 1/3 is just 3. on the bottom, the cubed root of 125. Which actually, those both have perfect cubed roots. The cubed root of 216 is just 6. I have x cubed. The cubed root of 125 is just 5. That is my answer. So they do this a different way than I do it. They actually rewrite it like 2 to the 10th power. You're never going to think to do it that way. So I would recommend just, even if it's a higher, to do your factor tree, okay? If you do your factor tree, even if you want to do larger number, that's fine. But if you do your factor tree all the way out, you're going to just keep going until you get... This is 8, 4. You're going to see lots of 2's going on here. Because I don't think you're ever going to recognize that that's a perfect guy there. So you're not going to recognize you have 2 to the 10th power. Like you're just not going to recognize it, okay? If you do recognize it, then you can rewrite it as 2 to the 10th power. That's fine. But if you don't, then you can just group it like you've always done. Group it, and then you have 2 left over. So 1, 2 can come out here, 1, 2 can come out here, 2 of them stay in. So I have 2 times 2 that came out, 2 times 2 that stayed in. That is a 4th root, 4, 4th root of 4. Lots of 4's going on. All right? If you have division, do them individually. Because I can't do them together. They have different index. Okay? I will say for this one, I would rewrite it. So 8 has a base of 2. What do I mean by that? I can rewrite 8 as 2 cubed. Right? Everybody see that? I can rewrite 4 as 2 squared, right? So if you see it has the same base, you may not see that 1024 has a base of 2. That's a giant number. But hopefully you know that 8 has a base of 2 and 4 has a base of 2. And so then I can rewrite these. That is 2. My numerator is 3. My denominator is the index 2. Here, my numerator is 2. My denominator here is 3. Now I can use my properties of exponents. I have like bases. All right, I have like bases. So if I have like bases and I'm dividing, I can subtract them. 2 to the 3/2 minus 2/3. Get a common denominator when I do this piece of it. 3/2 minus 2/3. My common denominator here is 6. So I have 9/6 minus 4/6. That is 5, 6. So that's my new exponent, 2 to the 5/6. All right. And if they wanted it back in radical form, let's say I wanted to put this in radical form. This is my index, my denominator. This is my numerator. The 6th root of 32. That's 2 to the 5th power. All right. So you're just going back and forth to make it easier to use them. All right. Easier to use them. If you want to use your exponential properties, then you can't do it in radical form. You need to convert it to exponents so you can do it, your exponential properties here. But you are looking for like bases.